I'm just so pleased to welcome everybody to Reunion, and I've met a couple of you already, and to this year's Engineering Research Talks. For those of you that didn't see the Dean's lecture because you were sleeping in or something, my name is Mary Wells, and I'm so pleased to serve as the Dean of this wonderful Faculty of Engineering. But really today is a chance for us to highlight some of the compelling and impactful research taking place within our faculty, and to show you how it connects to the broader direction of the University of Waterloo. And earlier this year, we released our faculty strategic plan. I talked a little bit about it in my opening remarks for the Dean's lecture. And in 2022, President Vivek Goel introduced this idea of the global futures. Again, I mentioned it in my talk. And it was really to help answer a bold, forward-looking question of what do we as a university want to be known for by our 100th anniversary in 2057. So it's clearly very far out there, sort of 30 years plus. And our shared answer really is that we aim to be known as the institution that not only tackles, but helps solve the most complex and urgent challenges facing humanity and our natural world. And Global Futures really gives us a structure for thinking about these challenges. It allows us to organize across faculties, collaborate more effectively, and focus our work for greater impact. And so the framework is really built around these interconnected futures. And that's the reason I'm giving you some of this background, is because when we look at the talks, we've tried to structure the talks in a way that connects to these global futures. So we've got 5 of them that are all different: societal, health, sustainable, technological, and economics. And these 5 futures really help shape and connect the work we do across disciplines, but they also provide a compelling lens through which to view the research you'll hear about today. And so each of the speakers that you will meet will give a very short presentation, 5 minutes. Now, for those of you that lecture, it's typically 50 minutes, but it's an order of magnitude smaller now, 5 minutes only. So try and stick to that, please. So, and on a current research project that aligns with one of the global futures, there will be time for questions at the end. Again, we'll only really have 5 minutes for the questions because we do have 5 speakers type thing. So, no, 4 speakers. 5 speakers, yes. 5 futures, 5 speakers, yes, of course. Thank you again for being here. I look forward to hearing your questions. And first up is Professor Amir Hossein Karimi to provide a perspective on societal futures. Amir is an assistant professor in the Department of Electrical and Computer Engineering and a Vector Institute faculty affiliate. He leads the Collaborative Human AI Reasoning Machines Lab, dedicated to pioneering advances in artificial intelligence to facilitate trustworthy, very important, human AI collaborations. The lab's research agenda includes developing AI systems that can ensure AI safety and ethics, rectify adverse outcomes, and synergize human and machine capabilities, particularly in domains like healthcare and education. So Amir, welcome. We're looking forward to your talk.
Okay. Can you hear me all right in the back? Yes? Good? Thumbs up? Excellent. Well, welcome back to campus for all of you. It's a great honor and privilege to be here for the second time. And apologies in advance if I can't stay for lunch. My girls are turning 1 today. And yes. So last year when I gave this talk, they were born a few days after that, twins. And yeah, we've had a lot going on. So anyways, let's get started. Oh, I guess welcome back to the classroom. Some speakers, including myself, and that's me. Excellent. So we're going to talk about towards trustworthy human AI decision-making, covering a bit of explainable, causal, and multi-agent AI-based systems. Also, if anything's unclear at some point, do shout at me. We have 5 minutes, but that's fine. I can just stop and talk to your question. That's absolutely OK. So right, AI. AI-based systems have proliferated various aspects of our daily lives, from healthcare to transportation, finance, and education. And as our dependency grows on these systems, a natural question to ask is, what could go wrong? And things could go wrong. So when ChatGPT or one of its APIs confidently gives you a wrong answer, you should be able to query its representation, challenge its reasoning, correct its answer, and all the while communicate with it in a shared language substrate. And although there is a need or a hunger by big companies for larger models and more performant ones, we argue that there's also an even more important need for additional systems and algorithms and processes that could detect issues, correct problems and suggest alternatives, and ultimately perfect the human-AI relationship. And so collectively, that is the mission of my lab, or the Collaborative Human-AI Reasoning Machines Lab, or the CHARM Lab. And we explore the following 3 questions. The first one is, on the detect pillar, how does one assay the safety, factuality, and ethics of AI systems to foster trust in AI? 2, how does one recover from or overturn poor experiences via decisions made by AI? And finally, how does one design systems that make use of the best of both human and machine abilities? And to answer these questions, we borrow insights from various subfields of AI, including explainable AI, which aims to answer why questions and promote a conversation about a system's predictions. Neurosymbolic AI, which blends learning and reasoning for models based on interpretable and widely accessible concepts. And finally, causal inference, which grounds these methods in the beautiful mathematical framework, also commonly used for a model of human cognition. Naturally, we collaborate with experts in multi-agent systems, psychology and cognitive science, as well as behavioral economics. So this is an open call. If you're interested in any of that, come talk to me at some point. I hope to have a good conversation about this. For the remainder of my time, I'm going to focus on one question, or one problem, which is the problem of algorithmic recourse. I'm going to just give you a taste of the contributions we've had over the past half-decade towards correcting behavior of AI systems, specifically where they go wrong. And to present this, I'm going to talk about a case study. So this is Edward. He's 28. He has a salary of $75,000. He's somehow managed to save up 25 grand. He's a software engineer, and he's single. This is, by the way, pre-inflationary period. Edward is looking to purchase a home. And after months of scrupulous savings and many open house viewings, he's finally found one he's interested in, but he has to visit the bank. Now, the bank may use a system such as this one to decide whether or not Edward gets the loan, or one like this, or perhaps one like that. And typically, as the models become more complex, they're better able to detect the nuances in the historical data sets, but they lose out on something important, which is that of their interpretability. So interpretability, or explainable AI, is defined as the ability to explain or to present in understandable terms to a human. And it comes with 2 important goals. The first one is understand why a particular decision is output, and 2, to recommend actions that would result in a desired output. One method in the past few years that has claimed to address both of these questions is called counterfactual explanations. They are statements like this: how the world would have had to be different for a desired outcome to occur. In the case of Edward, they say, if your salary had been 100 grand instead of 75, you would have gotten the loan. Unfortunately, though, counterfactual explanations fail to satisfy both of these goals, and therefore, we instead focus on a problem called recourse, which is defined as the actions, specifically the recommendations required for reversing unfavorable outcomes given by AI-based systems. This is a 5-minute talk, so we can't really go into the details, but here is a series, and for some reason this is redacted on PowerPoint. It's public out there if you want to view it on your own time. But through a series of works, what we show is, first of all, counterfactual-based explanations do not satisfy the goal of giving reasonable recommendations. In order to do that, we need to make very strong assumptions about how the world works causally, and it's really difficult to do that. So here's a practical probabilistic approach, again, redacted, apologies, a probabilistic approach for giving actionable recommendations to individuals that have been subject to bad decisions by AI-based systems. By the way, this isn't all pie-in-the-sky abstract research. In fact, if you go to the Directive on Automated Decision-Making put out by the Government of Canada, this isn't law, but it's very strongly recommended that anywhere we have a semi-automated decision-making system in some process, then if you scroll all the way down, recourse is listed there as something that the companies or institutions need to provide to the people subject to those decision-making systems. I'm sure all of you fully understand that we're not just talking about loans, we're talking about all of these scenarios, whether it's hiring, predictive policing, stratification of patients in hospitals. Wherever there's a semi-automated decision-making system, then we need to provide recourse. And the contributions we showed are just one of the things that the CHARM Lab is working on. Happy to take questions. And yeah, thanks for listening. Yes?
What can be done in the nearer term? You hear this term about AI hallucinations and getting incorrect answers, and it seems to be very prevalent. What's being done actively to try to counter some of that to help those who are a little less savvy in detecting some of these erroneous responses?
That's a very good question. And yes, hallucinations are something that, who's heard of hallucinations of AI systems? Okay, so most of you. For those who haven't, hallucinations just means that AI will confidently spit out something that is not correct, is not factual. In fact, it turns out that there's no solution to that. It's provably impossible to completely get rid of hallucinations. So the answer that I'm going to give you is not a technical answer, but one about AI upskilling in education. And that's something that we work here at Waterloo on as well. It's super important to educate users of AI systems into the potential issues that has. Hallucination is one of them. But there's a whole slew, unfortunately, or fortunately for us doing research, but unfortunately there's a whole slew of problems that AI systems have. One of them is hallucination. Yeah. Yes?
When you talk about like explainability of these kinds of models, does your work apply to sort of like the big, large language, the transformer model kind of stuff, or are you restricted to other, a smaller domain of machine learning models where you can do explainability?
So our work specifically, at least the past work, was not on LLMs because this predates large language models. But they equally apply to large language models as well. You could ask a counterfactual query saying, for instance, had this been different in my prompt, would the output have been different? That's also a counterfactual form of a query for large language models. In fact, now this is going a bit off topic, but I really find this interesting. We have something called search engine optimization, which has an entire industry involved. And people different companies want to do advertisement or want their website to be listed higher up in some search results traditionally on Google. But now we're moving away from search to generation. We're in an era right now where most of the population is chatting to get some results. And they don't get a full search result. They get 1 to 2, maybe, if anything, generated outputs from something like ChatGPT. Asking a counterfactual query there is super important for advertisers. What should I change on my website to be made sure that I'm the one that is generated there? So it's like search engine optimization on steroids. These are very important problems, and it seems like every day we have a new one come up, and the field is moving super fast. But if you're interested in investing, the Charm Lab is open to that. Other questions? Good question. Yes?
Very hand-wavy question, but anyway, 5 minutes. To what extent do you think the directions they're headed are inspired by actual human systems? So for example, in this example you gave, like in a real system, we have a banking officer with maybe an approver, and maybe an auditor, and maybe government agencies, and you have in adversarial, I'll say adversarial, but like people, checks and balances.
Yes.
Are these types of systems that you're talking about architecturally, I don't know, the current research, is it mimicking human-derived institutions, or are they different directions?
You said hand wavy, but that's an excellent question. The way that I interpret your question is, it seems like the problem that you're describing is not just a technical problem, but it's a socio-technical problem. Exactly. Absolutely. And that's one of the challenges here, and why I'm very happy that it's great to see a bunch of engineers, but also there's audiences that are non-engineers that should be part of this conversation. And these are not problems that engineers or computer scientists alone should be tackling, because the systems are not just engineering systems. In fact, you say like gaming or other types of strategic behavior that different agents within that system might employ, absolutely. If I'm a bank and the government tells me to do something, I could give a hand-wavy explanation to make it seem as if I'm abiding by the law, but actually not providing anything meaningful to that user. So how do we answer that? That isn't a technical question. So yes, I think you touch on a very excellent point, and the answer is not at least just falling within the domain of engineering. That's why we require this cross-disciplinary collaboration to make it happen. Yeah. Okay, I think I'm at time, but thank you for the questions and for your time.
Okay, thank you so much, Amir. That was awesome. Now I'd like to welcome Professor Lisa Anastasia DeCecco to talk about health futures. Lisa is an assistant professor in our Systems Design Engineering department and part of our biomedical engineering program. Her main research interest is in mimetic. Am I pronouncing that right?
Yeah, you got it.
Okay, all right, I got it, okay. Biomimetic implant development for medical applications. This includes hard tissue applications and fundamental biomineralization, is that right? Okay, I'm getting these words, okay, processes. She will be sharing some of the ways she and her research team leverage advanced multi-scale characterization tools to explore biomaterials with new lenses. Welcome, Liza.
Thank you so much, Mary, for that introduction. I did not wear a dress that had pockets today, so let's see.
That's clever.
Okay. I got this, yeah.
You can keep this here too if you want it.
Yeah.
Or
We're good.
Okay.
No, we're good. We're good. Okay. Hi, everyone. I'm so thankful to be here today. I'm actually one of our newer faculty members up here. I just started in January, so this is kind of like a part of my lab launch. And so I'll talk a little bit about how my team is engineering the future of hard tissues. And so a big part of this motivation for my group involves orthopedic implant needs. And so if we look at like recent statistics from one of the last studies that's available on our annual hip and knee replacements, these are over 117,000 of them replaced every year. I recently had a hip injury, so it's going to be something that I'm going to have in the near future. And when you think about this annually as a cost, this is attributing to about $1.26 billion. And this is just related to the surgeries and implantation itself. It's not including rehabilitation, loss of productivity, because we're often putting these surgeries off, as well as revision surgeries because of failures. And so that's really what I'm trying to reduce these needs and make longer living implants. And I'm not just focused on hip and knee replacements. There's many other bone implants that are similarly affected. Dental implants, spinal implants, cranial implants, and so on. But when we look at the commonality between why we often need these implants, it involves musculoskeletal disorders, things like osteoporosis, osteoarthritis, which impact the underlying bone quality and leads to degradation. And so one of the things that my team is specifically interested in is osteoporosis. This is impacting over 2 million Canadians each year. And this is on the rise. We're getting better and better at imaging and better at diagnosing these treatments. And what happens is typically with osteoporotic bone, you're getting more porous bone, you're losing bone density, and we're all engineers here. We know that would probably make it a little bit weaker. And so it's attributing to over 80% of fractures over the age of 50. Going forward here. And now studies are showing more and more that in osteoporotic conditions, they are associated to higher implant failures. And the big thing is there's known incurred risks. When surgeons are installing implants in osteoporosis conditions, they have to really be very considerate of the bone structure there. And there are treatments for osteoporosis, a common one being bisphosphonates, but these do have mixed results in bone repair. And as we're getting treated and earlier with osteoporosis and getting earlier diagnosis, we're starting to see mixed longevity results and things like osteonecrosis of the jaw, which doesn't sound so great. But the big thing is this isn't great for our implants, and our current treatment strategies aren't good enough. So driving questions for my team involve how can we improve osseointegration of implants in compromised bone conditions like osteoporosis. And then the other facet of my research that I'm interested in exploring is what are the fundamental mechanisms behind these calcium phosphate-based biomineralization processes that govern bone repair. And so I like to say I'm using material science approaches to answer these life science problems. So this is my new team. It's been really exciting starting, and we're called the Regenerative Biomaterials Innovation Group, or RBIG, and it's somewhat ironic because we're often looking at quite small samples of bone, but we focus on these three facets, which one involving biomineralization mechanisms, another biomimetic inspiration for implant design, and the last looking at liquid phase characterization techniques to natively image how bone and implants interact with each other. So I'm just going to share this little flavor of my work on the biomimetic inspiration side because 5 minutes isn't a lot of time, and I'm probably at 1.5 minutes left. So I'll show just some three kind of projects we have that are related to this. So the first one involves us answering, can we design porous implants to better match these implant bone sites? And so in this case, we're looking at biomimetic scaffold design to mimic the actual native bone tissues that are patient-specific. So I have students designing these very unique scaffolds and doing network analysis to compare what the networks of native bone tissues look like. And we're also working with collaborators to do these really unique numerical simulation methods to understand how our designs match similarly with the bone sites there and how they would fail. Another facet of my works involves how we characterize these new scaffold materials, because these are very new. They're coming up more and more in research nowadays, but we don't have very good standards of how to characterize them. So we're looking at producing these implants. We're working with the Multi-Scale Additive Manufacturing Lab on campus, which I think Michael Benoit will maybe mention in his talk. We're looking at surface analysis, micro-CT to look at internal voids that may be arising where failure could happen, as well as mechanical testing to check the fidelity of our models. And hopefully, I think my PowerPoint did freeze. This was a heavy animation slide, but the last facet involves looking at then producing implants with surface functionalization methods to enhance bone growth. So in that case, we're often looking at coatings that are already clinically used in other bone applications, but trying to understand how they could potentially be locally used for bone applications. So one of the coatings that you cannot see involves a compound called genistein, and it's actually derived from edamame or soybean, and it's a pseudoestrogenic compound, and it's totally natural. It's clinically approved, and we found out that using that as a local coating can actually enhance bone growth in osteoporotic conditions and bring it back to similar healing that native bone tissues have. So with that, that's about the end of my talk. You missed the last slide. But thank you so much for your attention, and I'm happy to have questions. You could probably just put it on my last thank you slide.
Question.
Oh, yes. Yeah.
In your talk, do you just focus a lot on bone density, or do you look at collagen?
Yeah, so in my biommineralization research, I'm actually looking at bone collagen and how it mineralizes and heals and repairs. And I'm looking at different metrics than a lot of doctors look at in bone applications. I think we froze it again. But on that last slide, I'm actually using these multi-scale tools, lots of electron microscopy paired with correlative metrics like micro-CT and other means that are used in clinical settings to understand more from the macro all the way to the atomic scale how that bone is healing and that bone properties and how the collagen looks like, if it's looking like normal woven bone or if it's disordered and chaotic and not healing properly.
And like which university or other kind of hospital kind of networks do you partner with?
So I'm brand new. I'm just actually getting a tour of Grand River, and I'm hoping to establish more clinical partners locally here. I have worked with collaborators and clinicians in Sweden, as well as I have a clinical partner in Brazil that's actually a dental research group, and they focus on osteoporotic and other disease models as well. Yeah, no problem. Wonderful question. Yes?
What's the scope of your research? Is it limited more to like mechanical type interactions in tissue ingrowth, or are you looking at bioactive approaches?
Yeah, I'd say I'm doing both. And so the mechanical side is definitely more in that facet of the design part of my research and looking at how we can change like structure functionally the implants to better grow into bone. But then I'm also looking at these bioactive coatings and seeing how the bone modulates and changes in response to different additives that we're using on these new coatings. So great question. Thank you.
Is one of your goals also to maybe identify some preventative measures? I mean, it's great, you know, if you could do better implants, but it's even more awesome if you don't need them in the first place.
Yes, that is a really good question. What's really exciting is I'm hired along with 2 other new biomedical professors, and we're all focusing on musculoskeletal systems. So I'm the preclinical biomaterials person. We have someone who's more on the clinical regulation side, and then we have someone post who's looking at gait analysis. And we have a large cohort now of musculoskeletal researchers, so I think there's a lot of opportunity to kind of put all of our brains together and start getting more into those directions collaboratively. So great question. Okay, one more. Sorry, I'm probably holding this wrong. Hi.
More of a comment. My dad had his knees done in '95, and I had mine done, and his implant only lasted 15 years, whereas I have had both my knees done, and mine will last forever. So keep up the good work.
Yes, exactly. Thank you. Awesome. Yeah, that's so great to hear. And especially if I need a hip replacement at a younger age because of my
That's even better than
injury.
knees.
Exactly. That one's really well studied, but we have to make all those numbers increase for all sorts of different bone implants. So thank you for sharing that. Thank you.
Yeah, thank you so much, Liza. That was great. We will now move on to sustainable futures with a presentation from Professor Maricor Arlos. Maricor is an assistant professor in our Department of Civil and Environmental Engineering and is also a proud U Waterloo alumna herself. What year did you graduate? Or do you mind telling us? Or 2011. So not, a signature year. Still a baby. Yes, still a baby. I agree. Still a baby. So in terms of the alumni, yes, I agree. So. Her research interests focus on the management and treatment of micropollutants in our drinking water, very important, municipal wastewater and stormwater. She'll share how her interdisciplinary background in environmental engineering, chemistry, nanotechnology, and ecotoxology enables her to assess micropollutant exposure, predict risks, and develop micropollutant mitigation strategies. Maricor, welcome, and I'll pass this over to you. Do you want to put that on there? Do you want me to help you?
Let's see. This dress has it has a pocket.
Oh, sorry. Okay, do you want to put it in your pocket then? Okay,
Yes.
perfect. Even better. All right.
All right. Can everybody hear me okay? Well, I'll just hold it. I'll just hold it, yeah.
Okay.
Thank you. Thank you very much. Very, very happy to be here. My focus is on mostly on the sustainable futures and how we mitigate organic chemical contamination. So the research that I do is on micropollutants, and these pollutants are found in the environment at extremely low concentrations. So think about parts per trillion level, so a drop in the lake concentrations. So they can be pharmaceuticals, personal care products, pesticides, natural and synthetic hormones. So basically everything, all the types of chemicals that we use on a day-to-day basis do end up in our aquatic environment. The reason for that is our wastewater treatment plant systems are not necessarily designed to remove these contaminants. And why are they important? So if you think about their concentrations, parts per trillion, so if you have 1 trillion balls, 1 red ball, 1 nanogram per liter, 1 part per trillion is the concentration of the red ball. So 10 to the minus 9. So that's the concentration that we're looking at. And they have an impact in the aquatic environment because they were made to be biologically active. So antidepressants are meant to deal with some of neurological, chemical instabilities in our brain. So they also would have an impact in fish systems or other systems that have similar types of receptors that humans have. So this is a fish collected upstream of a wastewater treatment plant. I would consider this as a handsome male, very colorful, you cannot see it, 2 lobes of white testes, very, very healthy male. And downstream of a wastewater treatment plant, you see these yellow blobs, and these yellow blobs are eggs that are actually forming in a male tissue, in a male testes. So we call this condition as fish intersex. And this is collected downstream of the Kitchener wastewater treatment plant back when I was still a baby grad student. And that really excited me in terms of understanding the impacts of these contaminants, even though they're present at low concentrations, the potential to feminize our fish. This is not the only one that kind of gets into the headlines. Their occurrence continues to garner attention. We have fish on antidepressants. We'd call it fish on Prozac. It actually impacts their migration patterns, right? Because their behavioral systems are changing. We have microplastics in their aquatic ecosystem. They're low concentrations, but we don't really know what their impacts are in our aquatic environment. So what I do in my lab, we look at ways to assess and understand their fate and transport. The first one is through really good and expensive analytical instrumentation that can measure concentrations down to parts per trillion, parts per billion levels. So really happy. I started in October 2024 here, and happy to see, well, I've been here since 2006. I left for a bit and then I came back. and access to these type of instrumentation really moved the research forward. I also looked at cell lines, exposed to cell lines. You collect water samples from the stormwater, from the drinking water, from the wastewater, and see what are the potential of these samples or environmental waters to cause some of these potential estrogenic effects, carcinogenic effects, and whatnot. And obviously synthesizing all of that information to a model so that we can give that as an information to our decision makers in terms of how they can actually use chemicals a lot better. I'm, for the last 3 years, I've been part of the scientific advisory committee for pest management in Canada, pesticides management regulation in Canada, and really hoping to give them a sort of an updated understanding of what the chemicals and their cumulative effects in our aquatic ecosystem. So when we use all of those tools, we find them everywhere. We just don't find them in water. We find them in sediments. We find them in fish. We also find them in bugs. These are some of the findings that's quite alarming because they don't have necessarily acute effects. They would have long-term effects that potentially have an issue with the growth and development and potentially the population and the biomagnification of these substances in multiple levels of aquatic ecosystem. In terms of treating them, there's many ways of treating them, but I focus on nature-based solutions. They've been around for 30 years, but not quite applied. And the reason being is, there's not a lot of applications, but I currently work with a dairy farmer out in Alberta, and hopefully we can reuse their water using constructed wetlands, and then they can reuse that safer water, polished water, back to their irrigation system. I'm also a big fan of circular economy, treating waste with waste. So if you know, Canada is one of the 4th largest aluminum producers in Canada, and it produces about 1.5 million tons of waste, and there's an opportunity for these materials to actually be used as wastewater treatment. So similar to the Brita filter that you have at home, these materials can be used as a replacement. I just wanted to move into this kind of take-away message in terms of enabling trends in sustainability engineering. It's really obvious that we need multiple disciplines in trying to tackle these issues. Transdisciplinary, cross-disciplinary, interdisciplinary approaches in terms of making sure that the way we live and the way we function as society is sustainable. And I want to bring back to that question of, what can we do and when can we change? I'm an environmental engineer, and I was taught sort of like points. Look at the issue, fix it, solve it, design a better treatment system. But perhaps we can look at the very beginning and look at, should we develop products that are much better to the environment? And that's obviously not the environmental engineer is not necessarily my role, but really an opportunity to innovate in that field. But sometimes when we keep developing these new technologies, yes, our water footprint goes down, our water is better, but sometimes our energy footprint also goes up. They require a lot more energy to treat our water better. So there's really these sort of questions that are not necessarily answered by one group of engineers, and perhaps not just engineers, but also multiple disciplines from different facets of our society. So I'd like to end there, and hopefully let's make waste together. And if you have any questions, happy to answer those. Yes.
You mentioned regulatory stuff around this microplastic space. If you think about like the sort of wave of environmental regulations in the 70s that did so much to sort of clean up the environmental problems before, they also had this sort of like knock-on impact, which was that it made it harder to do anything. Like the regulatory burden, this made everything go slower and be more expensive. How do you think about that kind of trade-off for this stuff?
Right, it is. Whenever you come in a room, you need to balance, especially for the watershed management, you need to balance economics, environmental, and also societal. So all of those things that would be able to answer and help the society or the community move forward. It's a very difficult question. You have a lot of sharks in the room, and it's sometimes a question of, and it's always asked, for me as an environmental engineer is like well, this one is not quite regulated, let's regulate it, these compounds are not regulated, let's go and focus on our healthcare system, let's focus on our education system. That environment stuff can go a little bit later. So it really comes down to the priorities of a certain community. So some places, like the EU, for instance, are a little bit more advanced in terms of, they try and talk to the producers that these are the rules that we have about chemical regulation. We need to do something about it. So it really does matter in terms of society, and unfortunately I don't have an answer to a one-size-fits-all solution to mitigating organic contamination. Sorry. All right. Well, I guess that's it. Thank you very much.
All right, thanks so much, Maricar. That was really interesting. I'd like to now welcome Professor Michael Benoit, Assistant Professor in Mechanical and Mechatronics Engineering, to help us frame technology futures. Michael's research spans many topics in the fields of welding and joining and metal additive manufacturing. Michael works closely with the newly opened multi-scale additive manufacturing facility. This is one of the largest research and development additive manufacturing facilities in the entire world, so it's outstanding. His talk today will highlight the use of additive manufacturing technologies to repair high-value metallic parts for the automotive industry, resulting in more competitive and sustainable manufacturing. Welcome, Michael.
Okay, hopefully everybody can hear me. Perfect. Okay, well, welcome everybody, good morning, and welcome back to campus. Today what I want to talk about is a bit of a revolution that's going on right now in manufacturing. But before we get there, I thought we would maybe start with setting the context with manufacturing in Canada and understanding why we're researching manufacturing. And as it turns out, manufacturing is a vital part of our economy. It contributes about 10% of our GDP and provides up to about 1.7 million high quality, well-paying jobs. And when we look at this sector, it turns out it's quite broad and it touches on many industries, everything from transportation to textile production, green technologies, biotechnologies, all these kind of things. But similar to any other industry or sector, in order for our Canadian manufacturing to remain globally competitive, we need to continue to innovate through new ideas and new technologies. And the new technology that I want to talk with you about today is this idea of additive manufacturing, also commonly referred to as 3D printing. Now, you've probably seen a lot of the 3D printers printing plastic parts are quite ubiquitous at this point, but today what we want to talk about is 3D printing of metals. Okay? And so when we talk about this idea of additive manufacturing, what we're really talking about is a number of related process technologies, all of which operate on the same principle that we're going to create a part from the bottom up, one layer at a time, placing material only where it's needed, okay? And when we compare what we can do with additive manufacturing to traditional processing technologies, there's a lot of benefits. So some of these would include expanded design freedoms, the ability to create incredibly complex geometries, reduction of material waste. We can consolidate a number of different processes into a single machine, and there's many more. We won't spend too much time on them. And on the slide here, we can kind of see some of the scope of what's possible when we look at additive manufacturing in terms of complexity of parts. So we have, for example, over here, this highly complex, we call lattice structure, to parts that are maybe a little bit less complex, but obviously the scale is much different. Here we're looking at a 40-foot bridge. Okay. Industries that they service could be anything from automotive, aerospace, biomedical, energy applications, and we can print pretty much almost any metal at this point as well. So there's a lot of potential with additive manufacturing. So you would think with the importance of manufacturing in Canada and the promise of these additive manufacturing technologies that it would be a slam dunk. Everybody would be using these technologies. But the reality is that when we look at the Canadian manufacturing landscape, it turns out that the adoption of these technologies has been relatively slow and relatively limited. And there's been a number of very good reasons that have been cited as why this is, and some of them can be seen over here in this list of this bullet point list here on the side. But it's my contention that if we're very smart about the applications that we pick and the technologies that we pick, there are opportunities for immediate a meaningful impact on how we produce things, okay? And so today, what I'm going to talk about is the use of a very specific type of additive manufacturing process that we call laser-directed energy deposition, or laser DED. And in contrast to some of the other printing methods that we have, laser DED can not only print new parts from the bottom up, but we can also use this to do things like refurbish, repair, and surface or clad existing components as well. So no, we're not only just creating new parts, but we're adding or doing value add to existing parts. And so today what I'm going to do is look through a case study where we use laser DED as a repair technology for high value metallic components. And along the way, I'm going to show how using this, we can actually make a strong business case. Okay, so we're going to do this in the form of this case study. So in this project that we're working on, we've been working on it for a few years, and this has a few more years left. But we're working with an auto parts supplier, a global tier 1 parts supplier. And they have a specific casting operation for aluminum casting. And in this casting operation, they put a piece of tooling into their mold, okay? And the tooling that they're using in this mold, it's very highly complex. It's made out of a very high strength tool steel. They produce very few number of these every year. So it's actually a prime candidate for the tooling itself to be printed. And it is printed by a technique called laser powder bed fusion. And that's great. The downside is that it becomes very expensive. So it's about a foot long, weighs about 40 pounds, but it costs them about $25,000 to produce a single insert. And so when I talked with the company, they told me that after a few thousand casting cycles, this tooling cracks. And when I asked them, okay, what do you do with that? They said, well, we throw it in the bin, get a new one. I said, okay, how many times does that happen? They said, about 20, 25 times a year. So you do the quick math, that's about $500,000 to $600,000 a year in operating costs from a single casting operation. So I told them, send us the insert, send us a damaged insert, and let's see what we can do with this, okay? So here we can see a segment of this piece of tooling. We can't show the full thing, but this is a segment, okay, of the tooling. Again, it's about a foot long, weighs about 40 pounds, made out of steel. And when we zoom in on this little area here, we can see the crack that they're talking about. This crack is what's causing them to scrap this component. If we look at the scale bar here, the width of this crack is far less than 1 millimeter wide. But it's enough that once it forms, they have to get rid of it. So what we did is we took this piece of tooling, we put it into our manual mill, and we just simply milled out a groove to completely remove the crack. And that's what we can see over here. So we just milled it out so that the crack wasn't there and it wouldn't grow any further. We then took this tooling that we had and we laser scanned it. And then, so we laser scanned the whole surface. And once we had that digital model of this tooling, we compared it with the digital model from the original piece of tooling. And by comparing the two, we could create what we call this sort of negative space model. And that's what we can see here in the green. So essentially, the comparison showed us where in our tooling that we scanned we're missing material. And so then we took this negative space model and we put it into our printing software and we created a print file here. So that's that yellow bit there. So essentially, it took this void in our part and we created a printable part. So we've segmented here and we created the tool path. And then all we did after that, we took the part, we put it into the printer, we lined everything up, and we essentially just hit print. It's of course not as simple as that, but we just hit print. And so we can see here is the tools in the printer, so everything's lined up. So this is where the laser would come out of in the powder. And over here is a still image from mid-print. Now the whole repair process from start to finish took about 7 minutes. So very fast. So here we can see the final repaired surface. It's a little bit rough, but it's not too bad as far as this process goes. And it's nothing that we couldn't take care of with a little bit of post-process machining. We did another laser scan to see if we had any distortion, because of course if we repaired it but we distorted it, then it's not a great process. The good news is we didn't have a lot of distortion, so what we're seeing here is a bit of roughness on the surface. And then we also cross-section it, and here we can see the full repair, and then over here around that is the original part file. So what did we learn from this? Well, it turns out that this laser-directed energy deposition additive manufacturing process could save this company over $500,000 in operating costs from a single casting operation every year. Okay? So that's good. It's good news for them. So the question is this whole repair process really that simple? And the answer is, of course not. If it was this simple, we probably wouldn't have a job. So now, this is where the actual research part of what we do comes in. So along the way, and as we continue to find them, we're running into many different challenges, or as we like to say, opportunities to investigate. But these are things related to the manufacturing, so misalignment when we put it in there, non-optimal process parameters. We have metallurgical challenges, so things like oxidation here. So you can see some titanium oxide, these brittle particles that have formed because of oxidation of molten metal. We We also have mechanical challenges. So over here we can see a hardness map that we took from the repair. So the repair is actually much softer than the surrounding parent material. So this is where the real work, or where the real fun of our job actually starts, is how do we address each of these challenges? How can we apply what we know to solve these challenges to give a meaningful solution to our industry partner? And that's where I'm going to leave it for now. And I'll leave it as just a quick thank you to all the people who did the actual work on this project, not me, who's up here presenting it, but had students, postdoctoral fellows, and some of our industry partners. And of course, thanking all of you for your time this morning. Any questions? Yep.
Why do you call it additive manufacturing instead of just 3D printing?
Sounds more industrial. There's no real difference. Yeah, they are really the same thing. Yeah.
What is a material that you wish you could print with but you can't today?
So I guess a big part of what I do is actually understanding what materials we can't print and how we can improve it. So a lot of our high strength aluminum alloys, aerospace grade aluminums, you can print them, but then they crack when we print them. And so a lot of what we do is also looking at ways that we can mitigate or eliminate the cracking. Same thing with nickel super alloys that we use in aerospace as well. So I spend a lot of time looking at defects in materials and how we can minimize or eliminate them all entirely.
Maybe one more question, then we'll
Sure.
move on.
You always use or try to use the same material that the original substrate is.
Oh, so yeah, this is a good question. So this this part here was made out of what we call a maraging steel. So it's Martin Citic steel, so very strong, brittle, but it's also age hardenable, so we can heat treat it in the furnace. So it's what we call M300 steel. The original insert, which is this area here, that's very hard in this case, was M300, printed by this process, laser powder bed fusion. The repair was also M300, but it was printed by this laser directed energy deposition. So we have a difference in the printing process, which affects the microstructure and then the properties. But part of the process of making the tooling initially is they print it and then they heat treat it to get that age hardening effect. But the repair that we're looking at is just as printed. So it doesn't go through the same aging heat treatment. So we do have this, and it's a challenge, and there's things that we can do at like sort of in situ heat treatments by running the laser more or less and understanding the thermal cycles that the material goes through. So yeah, but in this case it is the same material. Yeah. Okay. Thank you, everyone.
Thanks so much, Michael. Last but not least, up is Professor Horatio Morgan to help us think about our economic futures. Horatio is an associate professor of international strategy and entrepreneurship in our Conrad School of Business and Entrepreneurship. His research aims to help business leaders and policymakers forge new pathways to global expansion, innovation, and sustainable prosperity in a complex and dynamic world. More important today than ever, Horatio, I think. So, his core research investigates why some young and small companies innovate and expand globally, profitably, and sustainably. Horatio, do you want to come and get this?
Absolutely.
And then do you need the slide?
I think we do. Thank you. Okay, thank you. Okay, welcome back to campus. It's great to be here. I think it's usually safe to ignore economists, but not today, not today. Not today at all. I've been having some great conversations, as Mary hinted. We are not just speculating about the future, we are in the fight of our life for a Canadian future. And some of the things that I'll share with you, I had a session with the Privy Council Office, so that's the group of economists who advise the current Prime Minister. And so we are thinking a lot about what the future holds for Canada. And as economists, we like to start with a problem. And we are wondering if there is a business performance problem that could be holding us back. But of course, there is good news, and we should start with the good news. After all, we have outstanding companies, whether in natural resources, manufacturing, information technology. These are things to be proud of. And in fact, we are. But there are still opportunities to do better in some areas. And the concern, and certainly now, is that
we are not as competitively advantaged as we'd like when we think about, say, R&D spending. We are not keeping up in terms of converting our ideas into commercially viable outcomes. And there's a lot of research behind that. If I had to put it together, I'd say we have to do things on a larger scale when it comes to innovation and when it comes to launching businesses and scaling them globally. And we do a great job getting the ideas through the labs, but we have to convert those into actual products and services. Now, these are not just outcomes that are happening now. There is a past that really ties us to unique challenges. And the path leads, I'm not sure, we don't have enough time to talk about 400 years ago, but in a short form, we were once colonies with our American partners. The Americans were producing cotton in the global south. They were not expected to manufacture clothing. The British would do that. We were expected to catch beavers, get their fur, and the British would make the felt hats. We would supply lumber, they'd make the ships. That was what we were restricted to. And that was a very punishing system because it meant that we were restricted to being primarily raw material suppliers, not the ones that build the global brands, bring them to market. And so we are trying to really escape that sort of trap in this kind of, I would say, subordination. Michael spoke a bit about manufacturing, and we look at some of our best companies, Magna and Linamar. They happen to be doing a great job, but in the lower tier of providing intermediate parts that are later branded by an international car company. If we switch to a more complex chain, right, because again, we're not talking about companies producing things by themselves. I use the term global value chain to hint at this is a network of companies jointly producing things together. And the leaders in that smartphone, that would be Apple. So it designs the phone. It has components built in Germany and elsewhere, like Infineon. The parts are sent to, see, Foxconn in China. They're assembled, and they're reshipped at roughly $200. And then Apple almost magically brands that, and we have a product that's worth over $1,000. So the money's at the distribution end. And that's where we're trying to figure out how to get Canada there. This is what we call a smile curve. And it tells you that what's your position you're trying to take. If you're a great factory that's producing stuff, you'll notice that you're losing value. So you have machinery, you have some robotics, but there's a lot of competition here. Today, the value comes from using your data, algorithms, and traditional IP to actually guide your design. So are you designing specialized AI chips? Or are you using intangible assets to bring to market new business models and so on? This is where I would say American firms and certainly Chinese companies are looking to position. And we are somewhere here. Most of our industries were around here. So it means that we need to upgrade fast, very quickly. But upgrading is not easy. And it can be a source of conflict because other companies have an interest in the positions you take. So a lot of what we're thinking is what do we need to do right? We certainly need not only to make stuff, we have to own the intangible assets. We have to figure out to improve our positions in these production chains around the world. And so we have to think about strategies. I would expect our companies to think hard about how you compete. How do you achieve and sustain advantage in a marketplace? What's your strategy for commercializing your ideas and leveraging them? And of course, how do you plan to move on to functions that really generate high value and to become more central in these massive global networks? The hard part, and this is where the policymakers come in, because they ask me, what do we need to do? And there are a lot of policies that they can implement here. We don't have the time, but that's what we're working on, how we can actually bring businesses together to align each other on strategy and policy so that we can, in fact, create the future we deserve. That's perhaps a good place to stop, but we can continue the conversation outside. Yes.
I imagine the size of your local market, though, and I suspect that you kind of touched it would have been maybe under trading partnerships and such, right? Because unfortunately, you may have a great idea, a great product, but a country the size of Canada is likely not going to develop the kind of following that maybe a less good product in the States just because of the size of the US market, and then scale it up even more for China, for example.
Well, absolutely. In fact, if we look at the auto industry, there's not a country with a population less than 100,000 people, 100 million rather, from Germany and elsewhere. Well, North Korea is an exception, but for the auto industry, you need a massive population to get to begin to cover the cost of running these factories. But it means that we have to go global very fast to scale. And we're trying to remove provincial barriers, restrictions, and to see if we can actually test and validate our products a little early before we go global, where it's pretty wild and tough.
I suspect a bunch of us here, originally Canadians, have moved to the US, and one thing that I think is true of sort of the broad cultural differences between the two is that, like, the US is sort of more culturally a little bit entrepreneurial than Canada traditionally. So, like, how do you think that's true, first of all? And if it's true, it seems like that's like a pretty hard problem to fix with policy.
It's partially true. And one of the reasons is that it's more expensive to fail here. So we have a banking system, you provide personal guarantees to raise money, and we have not had enough experience taking risks, right? So when you look at that combination, if a founder fails here, your house is being mortgaged, and so it's more expensive to fail. The Americans very early, they gave a lot of relief on debt bankruptcy. So it's a combination of the cost of failure being higher and also lack of experience to really take risks with confidence.
Thank you. Thank you so much to all our speakers. We are getting close to noon, and I hope this has given you a little bit of an insight into the really important research questions we're working on from a range of different sectors, and how this research intersects with the biggest issues facing Canada in the world. And the speakers were amazing, and we're so lucky. We've hired so many really wonderful professors here recently. Thank you all for listening so much and sharing your thoughts and asking wonderful questions. Our speakers, except for Amir, because he's got to go to his twin daughter's first birthday, and if I were your wife and you didn't show up, I'd be very upset, so you've got to get there. That's all I'm going to say. They will be joining us for the barbecue, so please feel free to ask any additional questions that you don't get a chance to ask, because I know there were a couple more for Horatio and some of the others. So enjoy the barbecue, and the speakers will be joining. Thank you so much, everybody.